Good morning, everyone. My name is Nico Verwer, and I will speak about success factors and pitfalls of declarative techniques. First, let's have a look at what is declarative. I have shown here two papers from the 1990s, and the first one by Lloyd says that declarative programming involves stating what is to be computed, but not necessarily how it is to be computed. And that's equivalent to stating the logic of an algorithm, but not necessarily the control. And then Torgerson in the second paper says that declarative programming includes functional programming, various logic programming languages and extensions, and definitional programming, where definitional programming may not be known to everyone. It's kind of generalization of functional and logic programming. I've been able to find two definitional programming languages, GCLA from the 1990s and nucleoid.org, which is interesting because it uses JavaScript syntax. So why do we use declarative methods? Well, that's because creating software is complex business. And not only that, but several metrics suggest that programmer effort and therefore cost is proportional to complexity to the power of n, where n greater than 1, which means as the complexity increases, the effort and cost increases even faster, exponentially. And this is suggested by several metrics, the health state metrics and Kokomo, designed by Barry Bohm. Bohm also predicted that software costs would soon overwhelm hardware costs in the early 1970s in a report on the ADA project, which was a project to develop a modern programming language for DARPA, the Defense Advanced Research Projects Agency. And they expected that Bohm would predict that hardware would remain the biggest problem so that they could keep buying expensive supercomputers. But the report actually indicated that soon software costs would be far more important than hardware. And then we have Moore Switch, which was named like that by Stephen Pemberton in 2019 in his talk last year in this conference, who said that compared to the cost of a programmer, a computer is almost free. And Stephen gave a figure shown on the right, showing the cost of computers and programmers. In the early 1980s, the cost of computers dropped significantly, so that the cost of creating software was much larger. So what is complexity? In his essay No Silver Bullet of 1986, Frederick Brooks, who also wrote The Mythical Man Month, said that we cannot expect ever to see twofold gains every 2 years in software development as there is in hardware development, which also means that software costs at the time were overwhelming hardware costs. Now, software is complex because of two kinds of complexity, Fred Brooks argues in this paper. There's essential complexity, which is caused by the characteristics of the problem that the software is meant to solve. And this cannot be reduced, it's inherent in the problem. But there's also accidental complexity, which is what engineers create and can fix. And this is due to difficulties in the chosen software engineering tools, which is a wide range, and we've seen some improvement in that area over the last decades, and difficulties arising from the chosen technical solution. And that's something that I've seen in the past 30 years over and over again. Often this is caused by a lack of using a domain to frame the form of the solution. So then the question becomes, how can we reduce complexity? Well, by its nature, essential complexity cannot be reduced. So we have to reduce accidental complexity. But in most projects, it's accidental complexity that tends to grow over time. And we can reduce accidental complexity by using declarative techniques and specify what needs to be done, not how. And often the accidental complexity is in how the computer will carry out a certain task. And software architects and software engineers invent ever more complicated ways to do the how. Now, that does not mean that we all have to become geniuses to remove accidental complexity, but also we need to have a good look at what we're doing as software engineers. And that's because software engineers actually like complexity. It gives them a sense that they're doing something complicated and therefore important, and everyone else thinks that because it's so complicated, they're very clever. Also, software engineers think of themselves as software engineers, not domain experts, which means that they do not take the time and make an effort to understand the essential complexity that is intimately related to the problem they're supposed to solve. But instead, they will understand and create accidental complexity. That's what they're working on, and that's easy for them. And again, one source of accidental complexity, therefore, is the lack of using the domain to frame the form of the solution. As Gerrit Dijkstra said about this, why is elegance found so little following? That's the reality of it. Elegance has the disadvantage, if that's what it is, that hard work is needed to achieve it and good education to appreciate it. And the problem is not just software engineers, there's also the managers in software projects, and they think something like this: making software has always been difficult and can't change, and it will always be difficult, so the solution must be to make the software generic. Then you can do everything with it and you only have to make it once, and you just need to configure it for the task, some tasks that I don't even know yet. And sometimes I suggest that the most generic software is a C compiler, where the C in fact stands for configuration. Now, in my view, there's really only one big success factor of declarative techniques, and that's that they reduce accidental complexity. They make software development more simple for the programmer. And as Dijkstra said, simplicity is a prerequisite for reliability. Also, declarative techniques give you the right tool to work on problems in a way that's prescribed by the domain that you work in. And Dijkstra said about the use of language, it is impossible to sharpen a pencil with a blunt axe. It's equally vain to try to do it with 10 blunt axes instead. And finally, the competent programmer is fully aware of the limited size of his own skull. He therefore approaches his task with full humility and avoids clever tricks like the plague. Now, what are examples of successful declarative techniques? One is regular expressions. They were invented a long time ago by Stephen Kleene in 1951. And the idea was to describe what a neural net in 1951 language, or what we would now call a state machine, does, but not how. So in order to do that, he invented regular expressions. And here above my head, you see first a finite state machine with 3 states. One is labeled as start and one is finish. And there are transitions between, and this state machine recognizes the text A followed by 0 or more B's followed by a C. And you can also see the regular expression, which is simpler and which leaves out all the details of how to recognize this expression. And mostly regular expressions do in fact compile to state machines, which include a lot of detail that's unnecessary to the programmer. There's a really good video about this on the Computer File channel on YouTube, and here's the URL. Many declarative languages are domain-specific languages, which means that they operate on a very specific data model. But not all domain-specific languages are declarative, I like to say here. So examples are SQL, which operates using relational algebra on the underlying data model of tables and relations. And in SQL, you specify what you want to do, not how the computer will do that. We have XSLT, which works by pattern matching on the input document to drive the computation, to tell the computer how it does it. And you specify only the operations on the underlying data model of the input document. We have XForms, which specify an interactive view on a given data model. And again, you have operations on the underlying data model specifying what you want to be done, not how. And other examples are Link in .NET and GraphViz and Vega for visualizations. Now, domain-specific languages do not, by definition, reduce complexity and therefore effort and cost. So we also need to look at what are the pitfalls. I think two main pitfalls that declarative techniques may encounter are genericity and reification. Genericity is not being specific, so that something becomes widely applicable by configuration. And often when this evolves, it leads to a complex meta model, a lot of technical details, and eventually your configuration language becomes Turing complete, and you're defining a rather cumbersome programming language. Then there's reification, which is making an abstract concept or idea into an explicit data object, and you end up with objects that represent something else than themselves. An example is the data transfer object, which represents how an entity is stored, but it's not that domain entity itself. And ideally, we would want a computer to figure out how to store it. Having said that, DTOs were far better than the entity beans in Enterprise Java Beans before version 3.0. And in fact, Enterprise Java Beans is a prime example of accidental complexity. Now, as an aside, Enterprise Java Beans, we have this enterprise software, and there's a term enterprisey, which makes complex things seem simple by talking about them in a lot of complex terms that no one understands. And this happened a lot in the early 2000s. The heyday of neoliberalism, where companies thought that they only needed a good management structure and then they could outsource and offshore everything, especially software development. And then you would have someone cheap in India who usually didn't understand what you wanted, but they wrote a lot of software for very little money. And this led to software that followed Conway's law. It followed the communication structure of the organization. Everything is done somewhere else. You get incredible dependency injection hierarchies and a lot of boilerplate code. A lot of code that is not business logic, but that's just accidental complexity. An example is the enterprise service bus, or as Jim Weber and Martin Fowler once called it, the erroneous spaghetti box. So let's look at some examples. Around 2005, I worked for a company that had many content sources that it used for publishing. And at that time, there was a hype about integrating different content sources in a flexible and therefore generic way and doing multi-channel publication. So everything could be published to paper, CD-ROM, a website, etc. But of course, all these content sources had a different structure. And at that time, 2005, the XML files in these content sources had their own D2D. The management said, well, it's a waste to have all these different D2Ds. We need to make one overall D2D that can describe everything. And we said, yeah, but we need to have different validations. Yeah, but it's much easier, management said, to have one D2D for everything. So off we went, and something like this happened. The management said, make a generic something. This is a very generic slide about generic things. And then you only have to develop it once. And then the clever software engineer thinks, if I make XYZ an instance of XYZ itself, I can easily modify it and change it whenever the specifications change. And that led to genericity by reification. Describes something in something itself. And we called it the thing D2D, where a thing is something with things. So in XML, because this could describe any XML document, we have an element, and then an element contains 0 or more attributes and optional content, and it has one attribute called name, the name of the element. The attribute element is empty, but it has a name and a value, and content is a mix of character data and other elements. And below on the left you can see an example of what a simple slide would look like. Now this could express all the different content sources, so it's the most generic. It could be easily translated back and forth, and we never had any validation errors using this. And this idea can be applied in other contexts as well. So you can have generic, reified databases. We all know that database schemas are hard to change because you have a DBA and you need to file a change request, and it takes time and effort, and they never agree with your change. So alternatively, you could make the database within the database. You have 3 tables: field, table, and relation, and relations between them. And this would nowadays be called a software-defined database. I think you can make a lot of money selling those. As a bonus, you can even store your code in the database, so you can bypass the deployment process of your company. In RDF, reification is often used to make statements about statements. So here I have one statement: Amsterdam is capital of the Netherlands. But then if you want to say something about it, like this is said by DBpedia, you have to use reification like given by the 5 rules below, which is a description of the same statement. But if you have reified everything, it's really hard to query with Sparkle. Inference becomes difficult and very slow because you have to program it yourself. Accidental complexity. Basically, everything you want to do with this becomes very inefficient, unfortunately. Here's another example, not so much about programming, but the tools that we use in software development. You can do Scrum with TFS. Now, TFS has boards on which to place your user stories, but out of the box it only supports 4 columns: new, active, resolved, and closed. You can't really use resolved because only bugs can be resolved, but not user stories. So if you want to follow a Scrum process, you need to have active, review, tests, and closed. And how this was done in one project I worked on was we made subtasks of the user story for all the phases: active, review, test, and close. And then those subtasks would go through these different columns. If this sounds complicated, yes, it was. And it also led to inconsistencies. You can see that in the second row, where a user story has been tested, because it's already closed, but the review has yet to start, which is not a very good Scrum process. One more example, this time with XSLT. This was in a project where content went through 2 phases: analysis and enhancement, because that's separation of concerns. And the analysis would determine what function had to be performed on a specific piece of data, and then the enhancement stage would actually do the function. And in order to achieve this, the function and its parameters were coded as a new element, and that was passed to the enhancement stage, where we had to look up what the function was, lookup organization in this case, and then perform that function. Of course, if you wrote it in one XSLT, you could just have one function call and do that instead. So to conclude my talk, I've looked at genericity, which may seem to reduce effort. We've looked at reification, which may seem to provide flexibility, but more often than not, they lead to more accidental complexity. And I think declarative techniques can provide reduced effort and more flexibility by removing accidental complexity. And they do that by specifying what the computer should do, not how. But I think first, as humans, we should always ask ourselves why we do it. Thank you for your attention, and I hope you have an enjoyable conference.